Welcome to the third video in this series. Um, to, Today, right now, we're going to start going over the actual process of science. Previously, we talked a lot about the what is science. We talked about different aspects of science. We talked about biology itself, and we talked about how we can get emergent properties growing over a large, growing whenever we add complexity to a system. Now we're going to get into the process of science, actually using the scientific method, which is great because I feel you guys probably already have a grounding in this because if you're listening to this, you're likely older than 5 or 6 when we started applying this stuff in the first place. So without further ado, let's step right into the process of science. We've got two broad categories of thinking about science. We've got deductive reasoning and we've got inductive reasoning. Inductive reasoning is where we look at the general phenomena, which is sort of general, and you can predict an event based on that phenomena. So it's looking at a pattern and seeing what you think is going to come. And let's say the sunrise. The sun rose this morning. It rose yesterday morning. It rose every morning before that. So you can inductively reason that it will likely rise again tomorrow. You collect data, you see a pattern, and then you create a proposed solution to that pattern. Deductive reasoning works in the other direction. You're going to put forward a proposed solution and test it. You find evidence to support or disprove that proposed solution. So basically, you start off with a proposed solution, and then you test to see if that solution is adequate or not. In biology, specifically in this class, we tend to use deductive reasoning. Inductive reasoning is something that might be used in more animal behavior classes where we can look at a pattern and draw conclusions. In our class, we're going to test and retest to draw deductive reasons, a deductive conclusion. We got to get our terminology straight, though. We got to make sure we're all talking using the same vocabulary. And this ends up being a problem whenever you talk to somebody who's a non-scientist or somebody who's not necessarily in your field, and you're using words that are in your field in a different way than, say, the layman might use them. For example, a scientific theory. You, in your previous life as a layman, might say that a theory is just my best guess at something. I have a theory about who killed this, who committed the murder. I have a theory about how I can solve this. But in science, a theory means something entirely different. A theory is something that has been tested and retested and tested again, and the theory is our absolute best explanation based on lots and lots of verifiable evidence for a particular problem. So a theory is pretty darn strong. It's as close to a fact as we can get. One level above a theory is what's known as a scientific law. This is the absolute cornerstone of science. It is, if it fails, basically the universe as we know it falls apart. They have to be simple, they have to be universal, and they have to be absolute. There are no exceptions to laws. Because of that, we've really started moving away from the idea of calling something a law. Newton's laws of motion, for instance, wouldn't necessarily be a law in this day and age. Back in the 1600s, heck, even in the 1900s, we looked at things and said, we figured this out. We're humans. We absolutely understand the universe. But the more we learn about the universe and all of the complexity in it, the less we are sure that we are completely right all the time in every circumstance. For instance, we call them Newton's laws of motion, but do they hold true in the center of a black hole? Maybe, probably not, though. So a law is sort of this ideal in which it can never, ever be broken, or else the universe ceases to function as we know it. For the most part, in science now, we have theories. The theory of relativity, the theory of evolution. They are our absolute best explanations. To arrive at a theory, a scientific theory, you're going to use the scientific method. And the scientific method is sort of this iterative process. It's a cycle. It starts off with finding a question, proposing an explanation, then you test it. I keep saying that. Science is testable. After you've tested, you observe the results of the tests. You record them. You conclude whether or not to accept that explanation. And you let other people know about what you found. Usually, at the end of your test, when you've created a general conclusion, that conclusion will lead to more questions, which you then turn around and test, and the process begins again. By following the scientific method, you will end up adding to the general knowledge that we have about the world. So, let's do a quick example of this. It may not be as good because it's only on the screen. You can't see me moving my hands and flailing and running around the room. But looking at the screen, the first step is an observation. You notice something of interest about the natural world. Looking at the screen, you see a frog. I feel like I'm running sort of role-playing game. You see a frog. The frog has multiple limbs. What do you do? And that's the question. What do? You see a frog with multiple limbs. I don't know. First thing you might do is just whip out your phone and take a picture because it's frog with multiple limbs. But then what's the next thing you do is you ask a question. And the question is, why does this frog have multiple limbs? Especially if this frog lives in your neighborhood, you want to know what's going on. So you've asked the question. Why does the frog... Oh, you made an observation. The observation is, there is a frog with multiple limbs. Then, step 2 is you ask the question. Define the nature of the problem. The obvious question here is, why does the frog have multiple limbs? What's causing the frog to have multiple limbs? We want to learn that. Now, here's where people get caught up, because then there comes another step. Automatically, everyone wants to jump to, cool, now we're going to start running tests, because you're super excited scientists. But that's not the next step. The next step is do some research first. After you've seen this weird thing, you've asked the question why, the first thing you might want to do is Google it. Google's not the best place to find all the information, but it can get you a bunch of information quickly. Find out about frogs. Find out about frog life cycle. Find out about how frogs reproduce. Find out if there's ever been any other instances of frogs having multiple limbs. Other people have done a lot of research before you. You don't have to go it alone. Science is collaborative. We publish information so that other people don't have to repeat everything we've done over and over and over again. So look at all these resources. Now, when you're looking at resources, you want to make sure to use good resources. And good resources are, in general, peer-reviewed. These are going to be published in academic journals. Those are your best bet. And then you get varying levels of validity beyond that peer review, where other scientists have looked at it and either retested it or at least confirmed the methodology. From there, you might get, you look at professional sites, look at, conferences, look at moving down the chain. You might want to look at, say, news sites, published media, and then eventually you get down into the randomness stuff on the internet, like the blogs and the unverified material. And those are the places you don't really want to go for research. You might find something that says, frogs, 4-legged frogs, or 5-legged frogs occur because, I don't know, some mad scientist is stitching them together, or there's genetic manipulation that's causing this to occur. Really stick with the legitimate sources. All right, so once you've done some research, you can start to create a hypothesis. Now, your hypothesis is a statement about the way the world works. It's not a prediction. It's not an if-then statement. I don't care what they told you in high school. A hypothesis is not an if-then statement. It is a solution that needs to be testable and measurable. So what I would do in this situation is list all your possible hypotheses, statements about the way the world works. The frog has multiple limbs because it has a genetic mutation. The frog, multiple limbs in frogs are caused by a chemical spill in the environment. Multiple limbs in frogs are caused by, a parasitic infection. List all of your hypotheses down, all of your potential solutions. you'll notice that none of these are if-then statements. Your hypothesis must be falsifiable. That means it has the potential to be disproven by a test. Please note that no hypothesis can ever be proven or can never be proven. It can only be supported. A hypothesis can be disproven, but you can't ever prove a hypothesis. For the longest time, I have a background in philosophy. There was a syllogism that said, a philosophical argument that said, all swans are white. That was point one. All swans are white. Two, that is a swan. Therefore, and then it follows that swan must be white. And it happened, that was created in a time when all over the world there were only white swans. Well, it turns out after people got to Australia, because Australia messes everything up, there are black swans in Australia. The hypothesis has to be falsifiable. All swans are white is a falsifiable hypothesis. It could be shown to be wrong. How is it shown to be wrong? You found a swan that's black. No matter how much our current body of knowledge shows, there's always the potential for a hypothesis in the future to be proven wrong. I must have said this 1,000 times at this point. If-then statements are not hypotheses. You probably learned that to make a good hypothesis, you say, if this, then that. But that is a prediction about the future. It's a proposed, it's what you expect to see. They come after the hypothesis. First, you have to create your hypothesis, and then you can create a prediction based off that hypothesis. Once you've got your hypothesis, you can begin designing a controlled experiment. For ours, I'm just going to, normally if you were in class with me, I'd let you guys do all the work, come up with hypotheses, and we test them all. But I don't have you with me, and it'd be kind of weird for me to go through all the wrong answers. So we're going to test a solution that's quite simple, which is the hypothesis is multiple limbed frogs are caused by a parasitic infection. So we create a controlled experiment. This is a test that will gather data to support or refute that hypothesis. We get our frogs together. So that means we had to talk about what a controlled experiment is. A controlled experiment has a series of variables. Variables are just any part of the experiment that might change or vary. If we look here, we can see things that are changing and things that are unchanging between these two conditions. What's the same? You have the same type of glass. You have the same volume, amount of liquid. You have the same, height of the glass. You have the same temperature probably if they're in the same place. You have the same amount of light hitting it. These are all variables that could be changed. There are some variables that are definitely changed. One is clean, one is dirty. So dirt in the water is a variable that changes. But any of those variables could change. The variable that you are interested in, the one that you as the scientist manipulate, the one that you change, is called the independent variable. This is the one that you want to see having an effect. In this case, a scientist might be interested in the effect of dirty water on something. So the variable is the water quality. Is it dirty? Is it not dirty? That's the one the scientist is interested in exploring. That's the independent variable. For us, what we're interested in studying is the so we're looking at the effect of a protist infection on a frog. Our dependent variable might be the number of legs, because the dependent variable depends upon the independent variable. For us, our independent variable would be the presence of some protist, an infection or a parasite, So the presence of a parasite and the non-presence of a parasite. Two conditions. That's independent. That's what we're interested in finding out. The dependent variable is how many legs does the frog grow when they're in that solution. This is the responding variable. It changes based on the independent variable. So the easiest way to remember it is the dependent variable depends upon the independent variable. And the last group of variables are called our controlled variables. Controlled variables are all the rest of the variables. They're the ones that you keep the exact same. The temperature, the light, the amount of water, the volume of water, and so on. By keeping these the same, you can make sure that what's causing the effect that you see, what's causing the change in the dependent variable, is in fact likely caused by, the independent variable. So ideally, the only thing in the experiment that changes is the independent variable, and what you measure is the dependent variable. All of the other variables, we hope, are controlled and stay consistent throughout the whole thing as a basis of comparison. So now we got our variables set up. We have two groups that we're looking at in our experiment. We have usually our experimental group, and we have one or two or more control groups. The control group is the one that has every single feature about what we hypothesized about, every single feature that we're interested in except for that independent variable. We know that the control either will work or we know the control either will not work. It is our basis of comparison. The experimental group is the one that has everything that the control group has, and the independent variable was changed in some way so we can evaluate its effect. So for our control group with the frogs, we might have pure water, in which we don't think it's going to cause multiple limbs. Our experimental group might be water laced with some sort of parasite. Of our control groups, we have two types. We have a positive control and we have a negative control. A positive control is a type of control group in which we know for sure our independent variable will be impacted. A negative control group is one that we know for sure our independent variable will not be impacted. Usually the negative control group is pure water because there's nothing in water. So it's not going to react with anything. So you got positive controls and negative controls. The best experiments have both a positive control and a negative control. These control groups serve as a basis of comparison so you can see what effect the independent variable has on the whole system. Then you apply the scientific method. You gather data, and this data can be either qualitative or quantitative. You go out there, you figure out what's going on with these frogs. Quantitative data, like the name implies, is all about numbers. How do you quantify something? These measurements all involve numbers. Usually they're best for what we use in biology, physics, chemistry. The natural sciences tend to use quantitative data. How do you measure it using numbers, and then how can you run statistics on those numbers? The other side of this is qualitative data. This is descriptive, and they don't involve numbers. They're helpful. They talk about properties, but they're not typically as useful in natural sciences. They are often used in the social sciences. For us, quantitative measurements might be how many frogs have multiple limbs, or how many limbs do those have. You can talk about quantitatively how do you describe these frogs. Qualitatively, you might describe them as small or large or green or yellow. Or these don't have numerical values associated with them. Quantitative numbers, qualitative descriptions. Once we've gathered our data, ideally our quantitative data, we can organize that data into tables and graphs to look for patterns. Typically, tables are a way that we present our data at first, and then we can take that data and put it into a graphical format in order to really try and discover patterns that we see. And then finally, once you've looked at your graphs, you can draw some conclusions. You can accept or reject your hypothesis. And this is sort of important. You will legitimately, at the end of your experiment, say, I accept my hypothesis, the evidence supports my hypothesis. You cannot say my hypothesis was proven. It supports my hypothesis, or you'll say, I reject my hypothesis because here are the reasons. Make sure that every time you draw a conclusion, you support that conclusion with very specific data points. In our situation, we found that a protist, a parasite, basically, when the frog was a tadpole, as it was learning to grow, the parasite infected the area right where its legs were forming and did circles and broke those cells apart until multiple limbs formed. True story. After you've come up with conclusions, you need to take a critical look at your experiment again to really figure out your limitations. Look for possible flaws. Look for inaccurate data. Look for bias, especially if you thought something would happen and you impose that onto the system. Once you search for limitations, you can decide on the validity of your results and make suggestions for future improvements. You can come up with a new question. You can begin the process again. Finally, you've gone through this whole process. You say, my research was great, I'm brilliant, and you put it out to the world. You publish your findings. You give talks about it. You write a book. By publishing, other scientists can evaluate your data and support it or refute it, or use your information as the basis to form their own hypotheses, as some of the basis for their own research. So this is how science builds upon itself and how we have a greater body of knowledge now than we did 5 years ago or 10 years ago or even yesterday. All right, so you've got all the pieces of what a controlled experiment looks like. So let's look back into the past. I'm going to give you an example of how this was applied. And we're going to talk about this guy here, Francesco Redi, who's got sort of a horse face for him. But he did some important stuff when it comes not just to really solidifying the scientific method, but more importantly, figuring out a little bit more about where life comes from. What was observed in the past was that if a leaf lands on water, it becomes a fish. This was the thought pattern, right? If you've ever gone fishing, you cast your hook out into some leaves, and surprise, there's fish. And people noticed that leaves and fish look similar. Wherever there were leaves, there were fish. The ergo, that is, thus, fish come from leaves. People thought that mice came from bales of hay, because whenever you had a bale of hay and you shook it, mice came out. So the hay must be turning into mice. Mud, unliving mud, along the surface of a riverbed. People noticed that when it rained in the spring, the mud would bubble and frogs would erupt, and that's obviously to them because frogs are made of mud. And what they also noticed was meat turns into maggots. Meat hung in a market turns into maggots, which turn into flies. This was the world Redi was born into. Redi wanted to critically examine this idea of non-living matter becoming living matter, spontaneous generation of life. So he looked more closely at it. He asked the question, how do new living things come into being? Where do new living things come from? So he made an observation about the world. He asked, how does this happen? And he did a little bit of research. He observed that maggots appeared on meat a few days after flies were on meat. Now, he didn't have a microscope or anything, so he couldn't look to see if they were laying eggs. All he saw was a fly landed. A few days later, maggots appeared. So Redi believed, without seeing, that maggots came from eggs that were laid by flies. So how did he figure this out? How did he, without a microscope, how did he really identify that this was the way the world works? So he formed a hypothesis. Flies produce maggots. That is a statement about the way the world works. He set up a controlled experiment. In one group, his standard of control, his basis of comparison, would be meat left in a jar, just like out in the market, just like in nature. And you expect, just like he saw in nature, that flies would erupt from that meat after a few days. His experimental group contained the factor of the variable that had been changed. So on the other side, he said, cool, we're going to put a piece of meat, the same type of meat, the same cut of meat, into the same size jar, in the same temperature, in the same place as the other group. Except this jar also had a lid over it. What that lid did was it stopped flies. So he has one group that's a standard of comparison, just like in the market, meat that's open to the air, and the other group has meat that's in a jar that flies can't get to. So it was just all about stopping the flies from getting to the meat. The independent variable is the presence of the cover. The dependent variable would be the number of flies produced. And then he set these outside. He waited a few days. He noticed that flies landed on the meat that was uncovered. Flies tried to get to the meat that was covered, but they couldn't get to it. He began to collect data a few days later. And of course, the data he's collecting is the presence of maggots, or how many maggots are there. And if he's collecting numbers data, numerical data, that means he's collecting quantitative data. So he collected the data, he recorded the data, and what he found, of course, is that the maggots grew on the meat that was uncovered, and they did not grow on the meat that was covered. He created charts, he created tables, he looked for trends, and the trends showed, of course, flies on meat with no top, flies not on meat with top, or maggots on meat with maggots. He saw a distinct trend, he saw a distinct occurrence. He repeated that experiment over and over and found the same thing again and again and again. So he needed to put that into words. He analyzed the data, and he drew conclusions. To draw the conclusions, he restated his hypothesis. Flies produce maggots. And he accepted that hypothesis. He said there is evidence to support this hypothesis. Reddy's conclusions were that flies lay eggs that are too small to be seen with the eye. Maggots found on rotting meat are produced by the eggs laid by flies, and maggots are not appearing due to spontaneous generation, due to the meat turning into maggots, because if they were, then the meat that was covered would have turned into a mass of maggots as well. So this is a big deal. He'd suddenly showed that there was this whole new way of viewing how life comes about. It was, of course, instantly accepted, but it wasn't. Reddy looked at limitations of his experiment. He only looked at flies. He only looked at one type of meat. He only looked at the meat in this certain time of year, in this certain area. After he figured out those limitations, he published his results. His results were published in journals and seen all over the world. And what you might hope, what you might expect, is that scientists everywhere looked at this data, this one study, and said, my God, how did we miss this? Of course he's right. But that's not what happened. There was a back and forth. Changing a worldview is extremely difficult. As you've noticed in your life, once you have a worldview, it's hard to change it. So here's one piece of evidence that shows this. But other scientists didn't think this was the way it occurred. They thought that spontaneous generation, of course, happened. A scientist by the name of John Needham challenged Reddy's experiment. He designed his own that showed that spontaneous generation can occur under certain circumstances. What Needham did was he boiled what's called luria broth. It's this nutrient-thick broth that bacteria grow really well in. He boiled it, he left it open to the air, and lo and behold, bacteria grew in it. Everybody knew that would happen. What he also did was he boiled it. It's spontaneously the bacteria grew. He said, thus, spontaneous generation occurs. Reddy pointed out the flaw, which is, of course it occurred. You didn't put a top on it. My experiment had a top on things. Yours didn't. There's an issue. So a gentleman by the name of Lazzaro Spallanzini came along and he said, great, great. I'll prove to you, Reddy, that you're a jerk and I'm right. And I'm going to show this Luria broth experiment working. So he took Luria broth. He got it really hot. He put a cork onto it, and then he let it sit for a few days. And a few days later, sure enough, bacteria were growing in there. He said, ha! I have proven to you that life is spontaneously generated. But you guys have seen corks. What's sort of the overriding characteristic of a cork, if not, it's got teeny tiny holes in it? That cork could allow bacteria through, in small amounts, especially if that cork itself was not sterilized beforehand. So these experiments went back and forth. Over time, more and more evidence is building up for the rejection of spontaneous generation as a viewpoint. More people were recognizing that life doesn't spontaneously come about from non-living matter. It was ultimately Louis Pasteur, who you may have heard of from the pasteurization process, which this goes on to form, that spontaneous generation was killed entirely. What he did was he created this sort of this flask that has this swan neck to it, and that swan neck allowed it. So when you had a Luria broth or something that grows bacteria well, you can boil it. The steam could escape out of that vent, that swan neck, in one direction, and then but bacteria couldn't get back in because the bacteria would get caught in that little elbow, so they couldn't go all the way back in. He let that flask sit open to the air, but not allowing bacteria in for days, then weeks, then months, and nothing happened. Then he snapped the top off. 2 days after he snapped the top off, bacteria grew in it, showing that the bacteria didn't spontaneously generate, that they were naturally in the air. So it was really Pasteur's experiments that showed what Needham, what Spallanzini saw was not spontaneous generation, but the natural bacteria in the air landing in the broth allowed it to become filled with rapidly reproducing bacteria. This same process that you see in front of you on the screen is how we get milk that's pasteurized. We're able to heat it up, get rid that kills the bacteria without allowing new bacteria into the solution. So here's an example of a purely theoretical experiment going on to produce something that is wildly useful and practical. I guess that's a reason that we should fund some of the theoretical sciences so that we can end up with practical applications that really make our lives easier, nicer, and I don't know, in this case, lacking a lot of death. We've gone through a lot in this lecture. We've covered inductive versus deductive reasoning. We've covered the scientific method and how it works, how it's a deductive iterative strategy that goes from making an observation to forming a question to then forming a hypothesis and testing that hypothesis, gathering data, whether it's qualitative data or quantitative data, and determining the limitations of that study and then reporting out that information to the community. These experiments should be controlled experiments in which you have one variable that's changed, the independent variable, that will impact another variable that you're measuring, the dependent variable, and then all the other variables remain constant. These are known as controlled variables. You'll also have groups, a control group. That control group could be positive as a basic comparison to show you what would definitely happen because you know it will for sure have an effect, or a negative control that you know for sure will not have an effect. So there's a whole lot in this mini lecture that should help you understand the scientific method. Once again, these content review questions are here to sort of solidify your understanding, figure out what you might and might not remember from this particular mini lecture. We're going to be moving into the next set of lectures because we're at the end of the Introduction to Biology, surprise, And we're going to start talking about chemistry because chemistry forms the foundation of modern biology. So stay tuned for the next video in this sequence in which we begin discussing the magic of chemistry.